Started then. First, before I start, any questions from last time? Yes, please.
This is the main purpose of the clock to allow synchronization between activities.
That's correct. So the main purpose of clock is to introduce into the X10 programming model barriers, dynamic barriers. So synchronization you can get through when, using memory. And clocks are essentially a control construct that get you multi-way barriers. And actually, I didn't get into the details, but on the clock library, so clock is implemented through a library class, in fact, there is support for split phase barriers, which means that you can signal that you're entering a barrier, and then you have entered the barrier. And then when you exit the barrier, you can take certain action. So there is, so when you can signal that you've entered the barrier and then go on and do some work. You don't actually enter the barrier right away. So obviously you have to use that with some care. But there are some advanced computational techniques that allow you to overlap this kind of synchronization with communication. So the idea is, you let everyone know you're done with the local work, so they can come visit and inspect your local state, and you're fine. They will get the right stuff. And then you can go ahead and send communications to other guys. So this communication with overlap the period of time while others are gathering at this barrier. You don't have to lie idle. So it's an advanced technique for doing these things that you find in HPC systems. Okay, any other questions on clocks or anything else? Okay, I'm going to discuss today, the primary topic is to get to resilience, but before I do that, I want to give you at least a flavor of non-SPMD computations, and this will in fact bring me down a path where I'll go a little bit off script and talk about some technique for reasoning about distributed termination that in fact comes from my PhD work at CMU like 30 years ago, but is quite relevant in this context. So I'll do this brief segue into that stuff. Okay, so first let's talk about UTS. So most of the computations that we have talked about are SPMD. You get these large arrays, you break them up into pieces, and then you run activities that are reading and writing these local portions in that place, local portion of the data, periodically synchronized, then you communicate, and you keep going. Okay? But the whole point of X10 was to say that yes, we want to do that. That's where HPC code lies, but we want a general scheme, a finished async-based general scheme for doing dynamic spawning of activities across all places, no restriction on how nested your graphs can be, and so on. So what is a good poster child for that style of computation? So in fact, we sort of developed this whole thing without asking that question. And then when we did ask that question, fortunately, we had some ready at-hand examples. So let me describe this unbalanced tree search example. And by the way, I should have done this a while ago, but as I told you guys, I left X10 for a bit and I'm doing machine learning work now. And so this was a refreshing opportunity for me to go back and see where we are and so on. And that has sort of rejuvenated my personal interest in this. And I've started out an X10 research directions GitHub site. So you can go to my Saraswat, my ID on GitHub and look at X10 notes. And I've started out, the main page home has got most of the topics that we discussed. At this point, it's just a listing of those topics, and I will include there the references to the papers and summary of what are the top-level results obtained on each of those topics and links to the appropriate papers. So UTS is, in fact, plays a little bit of a central role in the development of X10, and it will show up in application frameworks and libraries, in particular in this global load balancing library. My Clicker, do you have that pointer? Yeah, thanks. Okay, so UTS. What is the idea? It's a very simple idea. N queens, any sort of state-based search. A lot of AI programs are of this kind. You've got some state, some small bounded amount of state that describes the state of your current problem-solving process. Might be you're playing chess, and this is the current state of the board, and you now make certain moves, and so you play out a whole tree of possibilities. You make a move, then you simulate your opponent making a move. You get from one board, you get a variety of boards, and you go down. It's a search tree. Okay, and your task is, thank you so much, and your task is to search that search tree. Now, when you generate a new position in the search tree, that position may lead to a varying number of new positions. So the first node leads to 10 guys in the second ply, then the first item in the second ply might lead to 2 guys, and so on and so forth, and it might actually lead to none, so you got leaves. So the UTS problem, unbalanced tree search problem, is to simply count the number of leaf nodes in the tree, right? So it seems like a very, very simple problem, right? How could this be complicated? Well, the problem is this tree is highly irregular. So it's designed to be highly irregular. And furthermore, you are asked to design code that works really well when you are examining a tremendous number of nodes in these trees, and you have available at your disposal tens of thousands of cores on multiple nodes. So you might ask, who the heck cares about this? Well, the security agencies care a whole lot about these kinds of computations. In fact, this was designed under a program, under some funding from some agencies in the United States, where this is taken as a distillation of a much more complex search problem. So unbalanced tree search, this thing came out in the HPC community maybe around 10 plus years ago as a benchmark. So what does it boil down to? It boils down to, first of all, you're working here with implicit trees. So you never actually ever construct in memory a tree. You only have a representation of a node in the tree, and this will have some state, and then it will have, actually that's all it will have. It will have some state, which is the way that we are going to ensure that this tree is unbalanced is that we are going to use this state as the seed for a random variable over some distribution. In particular, the guys in this space have used a binomial and a geometric distribution. So there are some hyperparameters for the distribution that are given fixed. So at each point when the time comes to expand this node, you use this seed to generate a value from a random distribution for which you are given some other hyperparameters, and you will get back n. That's the number of children in this node. N could be 0. So if you have n, then what you are going to do is you are going to create n children, and the way you create n children is, of course, by simply taking the state that corresponds to the root and appending 1 to it, and appending n. So sorry, I don't mean plus, I mean an append, and then take the SHA-1 hash of this. So the idea is it's going to be very difficult for you to invert this function. So you really have no way of predicting how complex your tree is going to be and how unbalanced your tree is going to be. And you can choose your parameters in such a way that you get severe imbalance. So the central task is you start at one node, you are given one, you start at one place, you are given one of these state vectors, and now you keep running. And you guarantee, of course, that the probability that eventually around any path you will end up, this is a finite tree, you will end up terminating. So you have a finite tree, and you are asked to count the number of nodes in this tree. This is the UTS benchmark. Is that clear? Okay, great. How do you do this? So I'm actually not clear what you have been doing with Guy. Has he taught you work stealing in earlier classes? Excellent. Okay, so how would you do this problem? So just, assume you're working on a single node. You've got many, many threads. How would you solve this problem? Any thoughts? You could try to statically divide the work up into those k threads available to you, but I already told you it's highly unbalanced. So what's going to happen to all those threads that don't have the big heavy mass? They're going to lie idle. You're not going to get great performance. So you have to dynamically distribute the load between these threads. How will you do that? So you could use a work stealing scheme. Works fantastically well, generally speaking, on a single node. But all my threads don't live on a node. I've got 1,000 nodes, and each of them has maybe 10 threads. Okay? So I now have to shift my work between these guys. How am I going to do that? You could do that. You could have a centralized node, and then everyone is hammering the centralized node. And instead of 1,000 nodes, I go to 10,000. Well, this scales so well. Okay?
For example, the passive amount of work, you can like propose the work to another thread, so like
good.
send them a proposal.
Excellent. So, so the claim. Sorry, your name? Evgen. Right? So the idea is that you could, you're a node, you've got work. Now, first of all, remember, you can't predict the amount of work you have. You have a node. You create his children, now you know how many children you have. So, okay, now you have some idea of the work. At this level, you don't have any idea of the recursive depth of this work. Okay, so you could maintain at each place now, let's go the circular place like this, you could maintain a kind of a pool of work being just these sorts of state vectors. Okay, and then you could say, hey, I am going to deal. Periodically, I'm going to push my work out to others. But who do I push to? I could choose a random guy to push to, right? So that's exactly the same sort of thing that you do in stealing. So stealing and dealing are two flip sides of the same idea. In stealing, the advantage is the guy who doesn't know what to do spends the cycles looking for work, as opposed to dealing where he already has some work, and then he's spending cycles distributing work. Well, that's not so good. So you want to steal. Okay? Good. How do you steal? Well, clearly we are starting out with, let's say, place 0 has the initial guy. And let's say we've started all of these places, so they're running happily. What are they going to do? They don't have any work. They need to steal. So they'll randomly go choose another place and ask, do you have work? If you have work, it'll try and divide the work up into 2, pick half the work, leave half the work. And so everyone is now hammering away at all other places. Okay? So initially, you drop this, piece of work in one place. A lot of these attempted steals are going to come back empty. Some will start hitting this. The work will start diffusing out into the system. Yeah? Yes. So again, the X10 programming model is you've got all of these places, and they're not necessarily on the same node. And so in between, you've got some transport layer, which, I should have said this at the beginning, which could be TCP/IP, but in fact on high performance systems it isn't. You use InfiniBand and you use, say, an MPI layer on top of the hardware abstractions given to you to get really high performance, both remote access as well as asynchronous data transfer between places. So all of that is available to you, but it is hidden inside the X10 constructs I have shown. So for now, you can just think in terms of how do you deploy the X10 constructs available to you. Okay, so you're going around, you are stealing. All right, so this could work in the sense that people, the work will distribute, people will execute. Nice. Now, there is no work left. All the work is gone. What's happening? Everyone is running around attacking everyone else. There is no work. Everyone needs to stop, but they don't know this. This is the active, what we call the active termination detection problem. Okay? So there are schemes. In fact, and this is my little segue. I'll come back. I'll just mention this. So Dijkstra discovered this little problem of detecting termination in what he called first diffusing computations. And diffusing computations he can describe quite easily. And so there's a paper by Dijkstra and Scholten that describes this beautiful little algorithm for termination detection. And it turns out this diffusing termination, this model of diffusing computation is actually very closely tied to the async finish model. So let me describe what it is. So you've got some bunch of nodes, n, in Dijkstra's notion of diffusing computation. And initially, you start with some node that has some work. All of these nodes are sitting there, they're passive. A node that has work is going to go active and work on it, do something. It might lead to sending messages to other nodes. Which other nodes, we don't know, right? So it sends off a message, and when a node receives a message, then it transitions from passive to active and starts working on whatever it is it needs to do, okay? It might recursively send messages to others. So this is why it's called a diffusing computation. It diffuses out over the whole grid. Now, the problem is to detect when all this work is done. So how do you do it? So they had this very beautiful, and they argued very nicely, establishing nice invariants for why this scheme works. And the scheme is actually very simple. The scheme is this. Whenever something goes active, and it subsequently receives, so first of all, the basic idea behind the scheme is every message that is sent will get acknowledged. Okay? And the whole trick is to delay that acknowledgement in such a way that the root, when it receives an acknowledgement for its messages, all its outgoing messages, it will know that there is no work left and it can terminate. So you want to take this global property that is a function of all the nodes in the system and convert it to a local property that one node can detect. Okay, this is the basic idea. So the scheme is, if you are active and you receive a message, you immediately acknowledge that message. If you are not active and you receive the message, then this is aha. This is the activating message. You will not acknowledge it till such time as you have finished acknowledging all incoming messages, and all the messages that you sent out have received acknowledgements. Okay? So roughly speaking, if you are sending out messages, you are responsible for detecting when the work initiated by those messages has terminated. Now you can see why when this initial guy receives responses to all of its messages, it knows that there is no work anywhere in the system and it can happily terminate. And it can go inform other guys to terminate. Okay? Yes? Exactly. So what will happen in our X10 way of looking at things is this is running a finish, and whenever it wants to send off messages to others, it's doing an at async to send out messages. That's the idea. The only difference is that in fact in X10 you're permitted to nest finishes. And Dijkstra-Scholten actually don't talk about nested diffusing computations. It's only one top level computation. But it doesn't take too much work to see. That's a pretty easy extension of their scheme. So roughly speaking, what you will now do is imagine that these diffusing computations have a color. Okay? So the initial one is whatever, some color. And now when you receive a message, you will activate just as before and keep operating as before on all messages coming in of this color. And when you execute a finish, now you will start a whole new diffusing computation of a new color. And you will go on and do the next thing, which might include sending the acknowledgement message back for the color which was activating this, only after you have received the acknowledgement for all the new colored messages you sent out. So in other words, a very cool property of the Dijkstra-Scholten algorithm is that it nests. So this gives you one implementation of finish in the finish async model, finish async at model across distributed places. Okay, very nice. Now, can I use this to detect termination for UTS? Yes? I can? How? remember, the critical problem here is that in this scheme, after you've acknowledged the message that activated you, you're passive, you're doing nothing. That's not what's going on here. Here, each of those guys is hammering other guys, still doing work. It's not doing nothing. And the central problem is to know that all of these guys who sort of, there is no, let me put it like this, there is no initiating in this scheme. There is no single initiator. They all started out simultaneously. So the need is to detect that all of them, again, global property, all of them have nothing to do. So you can't quite use this. So Dijkstra actually realized this. There's another paper, and again, I'll have all those links there. I did a paper, this thing that I'm talking about, I did a paper in PodC 88 on detecting, yes, I'm at least 10 years old at that time, so detecting stable properties of networks. And in there, I analyzed both of these schemes. So this was with co-authors, Udi Shapiro and so on. And I'll tell you the basic idea behind this paper shortly. But the point is there's another paper by Dijkstra and other colleagues, not Scholten, that talks about another distributed algorithm for this problem. So what is that algorithm? That algorithm, roughly speaking, works like this, except that you need to explicitly start a termination round. So you will imagine that you've got everything in a chain. You will say 0 will start out, let us say, and send a message to the next guy. The next guy is going to forward that message only when it has no work to do. Okay? So this way, this whole thing goes around, but unfortunately, when it comes back, there is no guarantee that there is no more work left, because there is a race condition between messages that might be sent by nodes that have work and the transmission of this token across the network. So, here it is sitting, doing idle, doing nothing. It has no local work. It receives this token. It sends it off to the next guy. But this next guy, before it receives this, sends it a message saying, here's work, or it sends it a message saying, here is work, continue. Okay? That doesn't. Now, you see there is a race condition, and so this is not going to establish a global property. So the algorithm says, oops, you've got to repeat this detection of termination rounds until such time as a token comes through with its color. So you color a token black and white, its color unchanged. And the idea obviously is that if you are going to flip through a node which was active, then the color would change. So I'm now skipping over because I'm a little bit hazy on this exact detail, but that's the basic idea is you change the color under certain circumstances, and only when the color is unchanged on the entire transit through that you know that there is no work and you can terminate. So this is the basic idea. Okay. Now, let me describe to you this sort of scheme, but in a slightly different way. Now I'm going to make a radical left field move and talk to you about distributed computation at a very high level of abstraction. Yes, please.
I want to suggest one thing. So can we, instead of using global queue for work, can
Yes.
we use a global queue to figure out which nodes have work and which nodes?
So there is no global queue of work here.
There is no global queue.
Correct.
We will create one data structure, and there are like 10 nodes.
Yes.
So one node has some X amount of work.
Yes.
We will put that, okay, node A has X amount of work.
Correct.
And then all other nodes will try to read this.
Yeah.
Then they figure out, okay, X have work. Then they will start communicating with that node.
Absolutely. The central problem is that everyone is working asynchronously. So there is, whenever you introduce this central notion, right, centralized notion, you're talking through the lenses of there is a time at this location at which everyone is operating. But that's simply not true, because this guy might check, another guy might check simultaneously. They'll get their own work spread out. So it's very, very hard to maintain a centralized global view of the entire state of the system. That's the big problem. How do you do that? How do you do that at scale when you've got 10,000 nodes running simultaneously? That is the essence. So this distributed termination detection is actually the heart of the problem. Once you solve this in a distributed way, then you can start building up these abstractions. Okay. All right, so I'm going to go down a very, very different path now, and I'm going to give you a notion of concurrent computation, concurrent asynchronous computation that is based on constraints. So here we have, these are all agents, places, whatever you want to call them. And we will assume, so constraints, simple things, we talked about them already, expressions of the form x equals y, x equals 1, x equals 0, x equals y plus z, those sorts of things. The beautiful thing about constraints is that I can actually assert something like x equals y plus z without knowing the value of x, y, and z. It's a constraint on these unknowns. So now our model of distributed computation is going to be that there is, quote, a store of constraints. In this store of constraints, these places can do the following actions. They can tell a constraint, tell C, or they can ask, is a constraint D true of the store? Telling is, you got some constraint, let's call it sigma. So telling is simply sigma is going to sigma and C. And so this is what tell sigma does. And what ask C does, this is what tell C does. And what ask C does is it does three things. It comes back and says fail. If it is the case that sigma entails essentially not C. It comes back with a success if sigma entails C, and otherwise it suspends. So this is the key to synchronization in this constraint-based view of communication. The beautiful thing about this system is constraints are accumulative. So once a store returns a yes answer to an ask, independent of what everyone else does, that will still be true. So you've got a sort of a stable property built into the infrastructure. So that 88 paper was showing that you can exploit this to detect distributed termination and a whole bunch of these stable properties. A stable property of a distributed system is a property that once it holds, will hold forever, barring some external intervention. Okay? So termination is such an example. So now let's see how you could detect termination in this case. So now let's do something extremely simple. We are going to imagine we have constraints available like a plus, which has in fact also a 0. So the only constraints I'm going to impose are of the form x1 equals x2 plus 3 or x1 is equal to 0. That's it. Very simple machinery. And the plus is not even important because I'm only, as you see, I'm only adding zeros. So the plusness is not important. I could work on any algebra which has a binary operation and a unit. And that will work. So what do I do? What I do is when I am sending out a message to someone else, so I'm active. If I'm active, I have my hands on a variable x. Initially, this thing that has the work, it has some variable that we're going to call z. Okay? And when the system is quiesced, when it's terminated, we will have the property that z equals 0. Anyone asks, is z equal to 0? They will get back a yes answer. So now we have to arrange our detection scheme in such a way that that is true exactly when there is no work. So now I'll give you what that scheme is. The scheme is this. When I'm sending a message to some other guy, then what I'm going to do is I must have a live variable. Live variable means something that is contributing to z. So let's look at the initial thing. Initially I have z. What will I do? I will conjure up new variables. I'll conjure up two variables, z1 and z2. I will assert this. Add this to the store. I'll keep z1 and I will send z2 in the message to the other guy. Now this other guy is active. Why is it active? Because it has a variable z2 that contributes to z through a chain of pluses. Yeah?
How do you know that Z2 is active?
Oh, by virtue of imposing this constraint, adding it to the store. Now my final guy z is z1 plus z2. I use that to define z1 is active, z2 is active. Because they are linked to the final variable through a chain of equalities involving pluses. That's it. This is the whole scheme. Now the other guy, when it gets a message and it is active, it will simply say, dude, Z2 is 0, nothing to do. It is not active, now it becomes active, and it keeps Z2. When it sends a message, it repeats this trick. That's all you need to do. Repeat the darn trick, which is this. So over time, your system is going to have a bunch of equations that normalize out to Z1 plus whatever Z29. If there are 29 activities running simultaneously. So the underlying infrastructure has the task of when these guys are equated to 0, now you can conclude Z0, now there's nothing left to do. So it's as simple as imposing two kinds of constraints. This is a splitting, and this is a shorting. And you use variables to hook them all up to this one guy, you're done. Okay? So that's in that paper. Now I can use this trick to also do the active termination problem, which is initially when the system has started out, everyone is active. Now I'll have place 0, send a message through to everyone, just like this initial circuit I talked about. But in this message, it is going to accumulate those variables. So here we've got these guys, each of them is active, so it will start out with some variables x1 through xn. They are not known to the system. No one knows that the entire system, no one knows that x is equal to x1 plus xn. We have to discover this. So the way we discover it is we send a message through, and each time that a message comes, independent of other messages in flight, it takes its current variable, whatever it is, Z29, and propagates. It will get on an incoming, it will get two things. It will get the variable that at the end will detect termination, we'll call that Z, and it will get some term T. And it will send out T plus its local guy, X29 and Z. It'll copy Z. So this way you're propagating Z to everyone. So at the end, everyone will ask, is Z equal to 0? And they'll all know it's 0, and they can terminate when it becomes 0. And you are building up all the way to the end. When this guy comes through, it will have x1 plus whatever, x29. It'll have all of these summed together in this expression. It also has Z. Now it says Z equals this. It imposes this constraint. Are you guys with me? Very elementary stuff. The beauty is we are leveraging the fact that conjunction is commutative and associative. Plus is commutative associative. So our implementation can leverage that fact. We actually don't need this for the logic to work. And it's just the timing of the imposition of these constraints that determines, by timing I mean after the local work is done, then you impose. That gets you into the situation where ultimately Z is 0 only when there is no work to do. Okay? More details you can find in that Pod C88 paper. We go through in a lot more detail on all of this. But the central, now let me come back to this UTS detection problem. Now, let's pretend that we did not know about this particular scheme for implementing. This scheme, it's a beautiful logical abstraction, but you still got to implement it. To implement it, you have to realize how this, the store of constraints is to be implemented. You have to implement these sorts of messages via ground messages that exchange, zeros and ones on the underlying infrastructure, so there's still work to do. So I'm going to leave this aside for you to think about and, explore further so the question here is, what kinds of distributed stable data structures can you build up using this sort of constraint machinery? That's the conceptual question to think about. Okay. Now we'll come back to this problem. So we have all of these fellows that are spinning around doing an async, looking for work by attacking others. And we need to know when they have to, when there's no more work to do, and now we can terminate the whole system. So finish is obviously what we want to use. But finish cannot work when the activities are busy doing something. So we've got to find a way to flip this, turn the active termination into a passive termination. How do we do that? Okay, so here's the basic idea. As before, we will start out with every place having an activity that's going to go try to work steal. But we want these activities to die because that's when the finish will trigger. Okay? So clearly the way to make them die is this. They try stealing for a little bit of time. They fail k times. And k is a parameter. You say, dead. You terminate. Okay. That's nice, but it doesn't load balance properly. Because all of these guys who have done these k things might terminate except for this one poor fellow who's got work and he keeps going. And now all your nodes are lying idle. So that didn't work. So you've got to do something else. And here's the basic idea. It's called lifelines. And I don't remember if I did this because there was this Who Wants to Be a Millionaire thing going on around this time. This was done around 10 years ago. Anyway, there's a lifeline. So what's a lifeline? A lifeline is before you die, you tell someone that you are dying. Why? Because that someone, so before you die, you hit somebody and you ask, do you have work? They have work, get back work, you keep going. You're in business, but they have no work. If they have no work, then you establish a lifeline to them. That lifeline is saying, whenever in the future you get work, give me some. I'm waiting for work. Okay? So this is a scheme that combines stealing and dealing. So now you establish these lifelines and you die away. Ultimately, if you are in a position where there's this one guy that has work, the guy will notice after doing a small amount of work, he'll notice, oh, I've got these incoming lifelines. Then its task is to deal some of its work to these outgoing lifelines. Okay? So this way you combine stealing and dealing, and this way you distribute the work from any one particular guy who has the work. So the question now is, what needs to be the property of this graph of lifelines? I could potentially have a lifeline to everyone. So first of all, for the sake of efficiency, you need it to be the case that if there is a single node in my entire graph that has work, then each of these nodes can actually reach this through lifelines. Because then the dealing is simply going to go follow that trajectory back. Right? You'd never want it to be the case that some node is unable to reach a particular node that has work. You don't know which node has work. So basically, you need a connected graph. So your lifelines have to be chosen in such a way that at the end of the day, you will get a connected graph. Not only is bounded for every node. Because if it is not, you will have nodes with a lot of incoming degree, n degree, and then the piece of work that you have, you may simply not have enough to distribute to all of these guys. So you want, again, some hyperparameter, k. So you want to bound the out degree by k. So you want it to be connected, you want to bound it by k, and you want to ensure that the distance, the diameter of the graph, the distance from any point to any point is low. Because that distance is going to be the latency, the number of hops that the work will have to jump through to find this place waiting for work. Many graphs satisfy this problem. And by the way, this does not have to be something you dynamically invent. You can hardwire this graph into your code. So there is a particular in our paper. So this is on the website. This is a paper in PPOP 2011, I believe, lifeline-based global load balancing, where we showed, this was the first algorithm to my knowledge that showed you can actually scale UTS to a very large number of nodes and get good scaling with no centralized data structures. So, of course, the point is now in this scheme, my top level, I do start out with a top level finish. So the top level looks like finish and then loop across all my places and go to an ATP and do an async. And this guy is the worker that's going to go a few times, do stealing, and then when it can't get any more work, establish a lifeline and die. That's it. That's the code. So the outer finish, a single outer finish will now detect termination because I've converted my active into a passive. And the key to all this is that the one single node that might be active with work has the power in X10 to use asyncs to create more activity at any node in the system. Just send a message to others. So to deal means that is going to come, the dealer is going to come to this target node and start an async there to start processing the work that is coming in this deal. Okay? Yes?
I assume that the runtime is still running on the other node?
Oh, yes. So the ground rules are the X10 computation is running on all of these nodes. Application code is not running. But the runtime implements the detection, implements finish and messaging and all of that. So that code's continuing to run.
Application waits now, but runtime hasn't done.
No.
Are you trying to terminate the runtime or just the application?
Oh, we simply want the application to detect that my work is done. And then the application wants to do things like print out the answer. The total amount of number of nodes is 2001 million, whatever. It can only do that after it knows that its activity has terminated. Or it might start another round. Whatever it wants to do, who cares, right? Yeah.
Why there are lifelines? Why can't just a node say that, okay, I have new work and give to one of the ideal machine?
How do you know, first of all, how does it know that a machine is idle? This is telling it, the lifeline is telling it that target machine is idle. Okay? So there's no randomly guessing and going to a guy. That's wasted time, wasted work. It's exactly being told there are all of these idle machines waiting for you. But now you can't have everyone waiting on a single node. You need this distributed waiting graph. That's what the lifelines accomplish. More question? The paper has lots of details and nice charts that show how much nodes are idle when you do these very, very large computations. So, you can look at all of that. Yes?
Is there any way to actually terminate the runtime?
Then the computation is gone. The world is over. Why do we care? I mean, yes, of course, you can terminate the X10 runtime. Now what? Now what do you do after that? You go home. There's nothing to do, right? Or you start another X10 computation. So that's actually an interesting question in the context of when I get to resilient X10. Then you will see that resilient is about a place going away. The flip side of it is a new place joining, right? So when you want to consume, particularly if you're operating in a cloud-based context, you want elasticity. You might be in a position where it turns out there simply isn't that much scalability in the code you are running. So you want to tell the operating system, Mesos, whatever, here, take some resources back. That is shutting down, the runtime on those places. And then you find you have a lot more work, you ask the operating system, give me some more places. So the resilient, elastic version of X10 supports that. That's the last piece that I'll talk about. Okay, so the question is actually quite interesting, what you just asked. Okay, any other question on this? Right, so let's, one last bit on this. So what I described is an idiom. It's a global load balancing idiom. UTS is just an example. You can do it for all kinds of things. So first of all, let me point out the much vaunted MapReduce doesn't solve this problem. You could think of UTS as a MapReduce problem, right? Except it's highly unbalanced. So what are you going to do in Hadoop? First of all, Hadoop is disk-based, forget it. We implemented in X10 a main memory MapReduce. There are slides all over the place which show tremendous improvement over Hadoop performance simply because we keep things in main memory, all our data structures, and we optimize for iterated execution. This was about 8 years ago. So yes, you could do MapReduce, but MapReduce assumes that the work being done in each mapper is roughly the same. That's not true here. So if your work in a mapper is unbalanced, you want to use this to balance that work out. So think of it as a global load balanced MapReduce. Okay? So this is a general idiom. What does this idiom need? So obviously what we want to do is supply it as an API, as a library. You can use this for our own computation, much as in MapReduce. You, the programmer, application programmer, simply specify a few pieces of sequential code. And the implementation handles the distribution, the parallelism, all of scaling, all of that. We obviously make sense to use X10 as that language in which you implement such APIs. So you do MapReduce. This is global load balancing. We want a GLB API. We did that a few years ago. There's a paper in PPOP, probably 4 or 5 years ago, that talks about GLB, the global load balancing library. And so the question to ask is, how do we abstract away from the details of UTS into a few pieces of sequential code that any application writer will need to provide to get their application to run within GLB? So obviously, the programmer needs to provide some piece of code that says, here is the initial work. Then they need to provide some representation for the bag of work at the current place. In this case, the bag of work is simply some bag of these state vectors. Then they need to supply a way to split a bag of work into two. Split, because when somebody is coming, they'll want half. And by the way, there are techniques, I mean, Guy may have gone into this, that, split half or you take one. Generally speaking, split half works well, particularly in this distributed context where there is a significant overhead to going off to another place through a message and asking for its work. So you split half. So you want to split, and then you want to merge. You want to take a piece of work from here, a piece of work, and merge. And then ultimately, each of these computations is producing some result. And just as we talked about a collecting finish, you want to reduce that result. That's it. So you supply about half a dozen pieces of code to initialize, to represent your bag of tasks, to split, to merge, to reduce. Do that, you've got, and run the GLB library over as many places as you want, and you have some chance of getting good performance out of the system. Okay, any questions on this? There is, when you download X10, you will get sample programs, and in those sample programs, there is a GLB library. Let's get this guy going. Hello? Where did you go? Oh, you're probably hiding in here. Nope. Does anyone know how to bring a...
It could be on other desktop.
It is. There are two desktops going on. The problem is I don't know how... This is supposed to be the one... Oh, sorry. I'm looking at the wrong one, of course. It's here. I just have to move it over. I thought I was displaying it, but I wasn't. Okay, thank you. All right, so there is GLB here. Come on. There is, in the X10 sample examples, there is a GLB library that has many programs written in the GLB style. And here, let me quickly show you. You can even do good old Fibonacci in this way. And it's not particularly pretty, but you will at least get, yeah. So you run from main, and you do a main test. So what will main test do? Here is main test. This is main test. This is going to create a new FibG and run it, and run is out here. This starts out a GLB computation and provides a start method, which is going to initialize the queue at the place with this thing, and you call glb.run with start. And this thing has various methods for doing the actual work, for processing, for merging two bags, for splitting bags, for doing the reduction. That's what you provide. Okay? So in the interest of time, I'm going to skip this. All right, so let me now come to resilience. So we have discussed the basic idea behind resilience earlier. Let me quickly recap. Here we go. That is not nice. Yes. What happened? Blah. That is pretty annoying. It was right there. Okay. That's all right. So I will just give me 1 second to see if I can recover. If not, then I will describe things without using this slide. Okay. No idea why it was not appearing there. Okay. So obviously we've discussed this before. The whole point now is we've got a full, hopefully I've now convinced you that this is interesting from an application point of view, a programming model that permits this kind of dynamic execution of task graphs with finish and so on. And now we want to make this work in a context where nodes can disappear. Places can disappear. Why? Because you're running in a cloud environment. Things can happen. Somebody changes the underlying operating system on your node. Your place is just vanished. If you're running a very long-lived computation, then you don't want to have that entire long-lived computation disappear. And in particular, in the high-performance computing world, people are going to even more powerful systems. Petaflop systems were 10 to the power of 15 operations a second, a tremendous number. That's when X10 started out. That's what the focus was. Now it's EXA systems, 10 to the power of 18 operations a second. And you do that by going to even lower voltages, on the chips, and you scaling out the compute infrastructure. And there are all kinds of possibilities of errors in each of these places. So you have to fundamentally start dealing with the possibility that errors outside your control are affecting the computation. So therefore, the way you surface this up in X10 is that a place can disappear. Automatically, asynchronously, a place is gone. So now, obviously, the original X10 system at that point would just abort. There's nothing to recover. It would say, there's a problem, and just go away. So the whole game here was to see, could we change the system, possibly redesign the language in such a way that this failure of a place is detected and surfaced back up in the programming model for the programmer to deal with. And hopefully not in a very complicated way. Okay? That's the goal of Resilient X10, with the idea that things like RDDs, you can then program, or things like MapReduce, you can program within the framework in such a way that they are tolerant to failures. And you can program other things. For example, some colleagues of ours have a paper out now on a resilient implementation of the GLB library. So such a thing exists. So the central point is that the program will continue to execute even if a place fails. Question is, what does it mean for a place to fail? Obviously, what is a place? A place is a vessel for memory, so that memory is gone. You no longer have access to it, the heap. And for activities running in that place. Those activities are gone. You don't have access to them. Okay? So that's what it means for a place to fail. Now, what we discussed a while ago was, fortunately, because of the design of X10, where there is an arm's length relationship between computation running in one node and computation running in another node, there is the possibility that we can detect and do something meaningful when a place dies. So here is place 0. For now, we will consider this special. And here are all of these other places. By the way, if you need to make a particular place resilient, you can always do that. The issue is you want to scale this out to, by resilient I mean tolerant of errors. You want to make your entire computation over 10,000 nodes be tolerant of errors. That is the conceptual problem. So the point is that how does this place interact with other places? The only way it can do that is in X10 there's just one construct, at PS. That's all, nothing else. So clearly, this construct now, its semantics needs to be modified. If this guy is going away, we will have the notion that an exception, a bad place exception, a BPE, gets thrown by this code. This exception is not special in any way. User code can do a try catch, catch it, progress, do something. Okay? And now all those things we talked about a finish being a point where you collect these underlying exceptions and throw them together, that comes into play. Because now all your finished structure you can reuse to recover from the problem that this place died. It throws an exception. That exception will be caught at a finish. It's not just going to disappear. And so the programmer can catch that exception and move on and do things. Okay. Yes?
So if one node goes down and the programmer gets an exception, then the whole code is exited or?
No. The whole thing is running. The code is at all other places which are not dead. The code that you wrote that's running is running.
So then automatically this workload will be transferred to another?
No. I'm coming to all those things. We start with the basics. First, detect that there is a failure and keep running. Okay? So contain that failure and keep running. So who will get this exception? Any place that launched an @PS. It could be this place. That will get an exception. So your code has to be written in such a way that it checks whenever there is an @ it now has to be written keeping in mind that that @ could fail. All right, good. So the @ has failed. Now what do you do? Well, before we get there, there's another important point to keep in mind. Fortunately, now unfortunately, the flexibility of X10 bites us. So let me just describe some simple examples. This guy starts out code here that comes to this place dies. Fine, that guy will get an exception, keep going. But what happens when this place started something here? So there's code running here and now it dies. You got orphans. I'm not going to go into the politics of child separation. Just you got activities that now do not have the parent. The parent context is gone.
Then it should go to the parent of the.
Thank you. I didn't pay you for this, but she's absolutely right. What do you do? Well, there are a few things you could do. You could say, well, that's just life. These things will keep running. But now, as a programmer, you've lost all control over your program. Because these things that are running are going to be mutating local state. And this thing could have started stuff everywhere. So you have no control over what is in your system anymore. Bad idea. Another idea is you could hunt those things down and kill them. Oops. You understand. Okay? That is very tricky. There are all sorts of race conditions in doing this. So the third answer is we keep it running, but now we rely on the fact that this is a rooted finish X10 insists on a rooted finish computation. Any activity running anywhere through a chain of finishes leads to the initial code running in the body of main from the thing that you called from the command line. So you can always dynamically chase back until you find a finish which is not on this place. And you reattach this child to the idea being that that finish will not complete until all of these children have finished. Now, that was going to be the case always, because they are within the scope of that finish. That finish would not progress until they are terminated. You're just preserving, even in the presence of failure, a property of finish. That was always the case. The point is, you cannot drop these. You have to attach them back. So this is the basic idea behind this principle that happens before invariance, which means that if in your program without failures, there are two instances of statements running with a happens before edge between them, or one statement instance running and another potential statement instance, not yet come into being, it's going to come into being in the future, but there is an edge between them. Those edges will be preserved even after failure. Okay? This is a little bit tricky to understand. The simplest way to think about it is that all a place does is it blows a big hole in the middle of your control graph. But we are now insisting that the X10 runtime maintains enough information about the parent-child relationship around finishes so that even if this big hole is blown, it can reconstruct that ancestor relationship and reattach those orphans. That's it. If it does, then there are no new race conditions. If your program has race conditions, it will still have race conditions, but failure does not introduce races. This is the big deal behind happens before invariance. Okay, so let's see what have we captured and where are we. Yep, so we are here, HBI, we've done this. Good. Now we come to the question that you asked, which is, okay, so we failed, now what? Well, now the initial design of resilient X10 said it is up to the programmer to repair application level state. Why? Because there are many different strategies you can take. If you're doing the so-called approximate computation style that Martin Reinhardt has talked about a whole lot, then you say, I don't care, this thing is gone, it's gone. I'm going to take no corrective action. And for some styles of programs, that's totally fine. Other styles of programs, you may want to say, oh, I'm going to periodically checkpoint the state of each place. And now that I know this place is gone, I will recover the state from that checkpoint and reestablish my computation. Okay? Or in another alternative strategy that you might adopt is one that says, I'm going to reconstruct this data, not from a checkpoint, but I have some way like RDDs do. They keep track of the history by which data was created and simply rerun that history to recreate this data. So there are many different strategies. We leave it up to the programmer to do this. Now, this sounds good, except for the problem that in fact this becomes a little bit tricky. So our goal of trying to handle most of the problems that arise with failure is only partially met. The user still has potentially fairly tricky code to write to rebalance the data that remains across the remaining places. Okay? So before I go into that, let me show you what some code looks like with resilience. So these are example programs that you will find in samples. And let's start with something simple like this. Okay. Right. So okay. Let me quickly go to another point, which is that as I was saying a little bit earlier, it makes sense when things disappear to design your programming system in such a way that you can make things appear. so elastic. So you want to say create a new place. Okay. Now, how are you going to do this? There are a couple of different ways. For sure, you want to support some external mechanism. So this means when you start an X10 computation, you get back some kind of a handle on the whole computation, which is some pattern of bits. And then there is an X10 registrar running. From outside, from a command line, you can say, oh, Mr. Registrar, here is the computation I care about. Please add this new place to it. So an external mechanism for attachment, you want that. And then internally, you might want to say, please create a new place. So that is supported, and if that is supported in the latest version of X10, X10 2.6 and 2.6.1. So you can, in fact, create new places inside or outside, and furthermore, you can attach handlers that get executed when a place is attached and when a place is killed. So you can, so here is a little handler, system.register place added handler and a place removed handler. Okay, that's what these pieces of code are doing. Now let's look at these other codes. So, you get to set an X10 resilient mode. 0, it's not resilient, it's going to fail if a place fails. 1, it will not fail, and the stuff that we're talking about comes into play. So you get to set that separately. And now here's a little piece of code where we are trying to show you how elasticity would work, how resilience would work. So obviously, it is a little bit hard to write code which requires you to walk up to your computer and pull some plugs in order to kill a place. So it's much easier if you have a kill here. So there's a kill here, system.kill here, which will kill the current place. Right? Use carefully, use for testing. Right? So that's here, system.kill here. Okay, so this is a little piece of code that, what does it do? It will, it will go through a loop. Ouch, what did I do? Yep, thank you. On line which? Where did I put in this extra character? Oh, it's very easy. Let's kill it and start. Killing is useful. Yes. Okay, here we are. Okay. So this thing is just going to do something silly. It's going to run in a loop on multiple places, and it's going to run that loop count number of times. It's going to run the basic thing. The basic thing is you go to all of these places and you inject failure in these places based on some random variable, next boolean, and then you say I'm dying and whatever. Okay, and you also attach those handlers, so you want to see that that's going on. Yes, please. Let's see. So once the place is killed, it's gone. There's nothing you can do. Okay? Here, you are doing the killing, so you can write out a message saying, I'm about to kill. But in real life, the killing is happening asynchronously. So you've got to recover after the fact. All right? So let's do this. Let's run this. And we will run this, and so I should actually, before I show you this, let me show you the parameters. So here I'd set this up. Where is this guy? Hello, whole world. Ignore this guy. This is this fellow. Ignore this. Hello. That's not nice. Why are my program arguments not showing up? So you know what we can do? We can delete this configuration and now this thing, and it is going to it wants message, loop count, and interval. This is what I wanted to show you. So we will set up the value here to be, let's run it 4 times. And what does it need? Oh, it needs a message. Let's get a message here. I am alive. Then it needs a loop count, so we'll say 4 and interval, say 100. And let's go here and set up X10 and places to be 4. And what was that? X10 resilient mode. And set this to 1. Do an OK. Let's verify if that was what. I believe that is what it wanted us to do. Yeah. Okay. So now please ignore the illegal reflective access. That should get fixed at some point. Place 0 sees 4 places, and it says hello and I'm alive, and then it's iterating through its loop. Place 2 comes online, says hello, I'm alive. Then 3 says I'm dying. And in the iteration 0, and then 1 says hello, I am alive. So 1, 2, and have come in and said they're alive. 0 is alive. 0 will now see that place 3 was removed, and it will also get dead place exception from place 3. Let's show you this little code that's doing all this. So here, so place 0 is the one that spawned all this code here, and it catches a multi-place, and here it's where it says got dead place exception from this place in the given round. So that's this thing printing out a detection that place 3 has died. And before that, this handler ran here and said at place 0, I see that place P was removed. And before that, as we should have, we got place 3 is dying. That was this happening at place 3. Okay? Now place 0 comes back and makes this call in the next loop around. It comes back and it makes the call to place.places, and that now returns 3 places. Originally we started with 4. So place.places had returned 4, and that's how you saw this. Place 0 sees 4 places. Now the second time around in the loop, it comes back and sees 3 places. And you re-execute this stuff. Now place 0 says, hey, I'm still alive. Place 1 says, I'm dying. Place 2 says, I'm dying. 0 again sees that 2 and 1 were removed. And it gets a dead place exception from place 2. And it gets 1 from place 1. And now it sees only 1 place in the next round. It says hello and I'm alive, and then it sees only 1 place. And by the way, the reason it doesn't die is because we put this in there. So we made sure that the place 0 doesn't die in our application code. Okay, so this is how you would write code, which detects when places have disappeared and takes certain actions, and which will then recover from these things. Okay, let me show you, what will I show you? There was a UT, no, I don't want to show you UTS. Let's do this. This is the simplest thing. Yes, go ahead.
About the earlier example,
yeah.
The new places were introduced at the start of?
No. No. There were no new places introduced. The program started out with 4 places. That's what I showed you.
Okay.
N places 4.
And how the places variable is managed in case where new places get added or something?
I don't have code for that here. So we'll have to dig this through. So it is in the current X10 implementation, and it'll be in the documentation. And there'll be basically, there's a system.addPlace, and there's a system.addPlace and wait. So the addPlace will instruct the system to create a place and return without having created that place, and addPlace and wait will wait. Okay. So if you want, we can very quickly try this and see what happens. Let's go back to 2, kill here. And it will do, and now we'll have it print out console.out.println creating a new place. And we will say system add place. Wow, there is such a thing? No, there isn't. Let's quickly do here. I need to know this guy. Aha! System.addPlaces n. Add places and wait. What is n? Let us pretend n is 1. Oh, is it a place ID? That would be annoying. So let's pretend it is number, which doesn't make sense. So we will actually ask it. And yes. Okay, what is add places? Here is add places. Request a lot to create n additional places. Can you believe that? Why one? You can create many. So let's just try to create one. Okay, so 1, and let's save this down guy, and we'll let's do it synchronously. Add places and wait. Add places and wait, and there's a timeout. Thank you very much. That's great because you don't want to wait arbitrarily long. All right, and so we will say here console out println done creating place. Okay, let's see what happens to this guy. Okay, let's see, what did it do? I'm alive, 0, 1, 2, 3, alive, alive. 2 is dying, 3 is dying. Creating a new place, done creating a place. And, and that is because it received 2 places died. 2 places died, but they died within the same loop. So it got 1 multi-exception, not 2. And we caught that exception, but we created a single place, not 2. So you see here, it created 1 occurrence of created a new place. And now what do I see? Why do I get, it sees 2 places? I should see,
I think place 0 and the newly created place, so that counts for 2 places.
0, 1, 2, 3, and then 2 and 3 died, so 0 and 1 should be alive. And then I've created a new place, and so place.places should see that. Why is it seeing only 2 places? I see that place 1 was removed, so that did not work out, which is annoying. Let's quickly take a... Yes.
New places created, place.places.
So it returns a long. oh, this launcher cannot, our Java launcher may not create a new place. That is, let's see what it returns. Okay. Launcher added. So let's print out. Okay? Zero, unfortunately. So this launcher, this was started under a launcher that is not supporting place creation. It returned a 0, it returned a 1. I will need to get back to you guys on which launcher can I start Java computations with. Probably the MPI. So I should finish by telling you that, let's go back here. And this last bit. I never showed you all of these things. The page that I was on, there are basically, actually now they're getting to be an increasing number of papers on Resilient X10. The original one, PPOP 2012 or so. No, 14. Then there was a paper we did on the semantics of Resilient X10. And that's the one I was showing you some, flashing briefly some slides from. That was with Sylvia Crafa and a bunch of colleagues. And this is that paper. The semantics of Resilient X10. In this paper, what we did was present a small step operational semantics for plain X10, and then for the resilient extensions of X10. And Avi Shinar formalized the theorem that we proved here about happens before invariance is preserved in Coq. And that was non-trivial, actually, to do that because of the problem that we have a dynamic heap. So we've got to show the property holding in a dynamic heap. So these are the two papers. Then there's a third paper, which is currently been submitted to a journal and is awaiting reviews. And that's where we show how to add new places. And that's been in the X10 release that was made. Then other colleagues, Claudia Fori and team, they have done the resilient version of global load balancing library. And then Sarah Hamoud and company in Australian National University have done a version where they show that this iterative SPMD, resilient iterative idiom, they've shown that it can work very well for high-performance computing codes as well. So the scheme that I talked about with detection of failure of places, we showed that there is this SPMD, resilient SPMD idiom, where you can take your so I should have told you earlier, the code that you have to write to handle resilience on top of the basic stuff is not a whole lot. It depends on your recovery strategy. But you can write your SPMD code in such a way that that is not a whole lot, besides checkpointing, which is application dependent. So there are papers, there are about half a dozen papers now on this, and more papers coming that talk about different properties of resilient X10. Okay, we are out of time. I'm happy to take more questions, but I'll let those of you who want to go. Thank you so much.